Morning, everybody. Mr. Stewart here, and welcome to the screencast. This will likely be one of two. Okay. Today's lesson is about the probability um, of particular events involving sets. Okay. So it was mentioned last week we would be exploring the use of Venn diagrams as a graphic organizer that would help us to solve probability problems. So here are the three objectives of the lesson. You will identify mutually exclusive events from other types. So that's going to come up through our lesson. We're going to represent events using diagrams, specifically Venn diagrams. And later on, we'll be using tree diagrams. And thirdly and lastly is to solve problems using what is called the additive principle for counting. Okay. So this particular first video is going to start off with the Minds on Math. Now, depending on where you are in terms of your work in preparation for class, you might be able to skip some of this material over and focus more on the latter part of the video or the second video. Okay, I won't spend too much time on the Minds on piece because we want to make sure that we are digging into that in the classroom space if at all possible. So you went ahead and tackled at least one of the three problems, and we would have solved them and or demonstrated them in class. So what I'm going to ask you to do is, if you have done so, is to perhaps hold off on the viewing of the remainder of this and maybe move on to the second video. You can always come back to this one for additional support. If you've been away and or you are in need of some background information on these, this would be a good video for you to watch. Okay, so what I'm going to do is one by one is model some of these three options. And again, if you're away, it's always best to challenge yourself to try the problem first, see what previous knowledge you happen to have. You'll find that a lot of probability is intuitive, and your methods also are quite good and strategic. So with your previous learning, try it out, and then we'll have a look at the solutions. So let's move forward with that. That is assuming you've given it a try. So first one deals with the roll of a die and then the flip of a coin. So you can see that I've constructed a tree diagram. So the first event is the roll of the die. The second event here in the second column is the flip of a coin. Notice that these two events, they are both simple events, together compound, but they are independent of one another. So that is to say, the flip, or the outcome of the flip, is not dependent upon the outcome of the roll of a die. So when you look through at the outcomes or the compound outcomes, we are looking for both an even roll of the die and the flip of a tail. So 3 of the 12 possible outcomes, or 1/4 of those outcomes, are specifically the event that we are looking, or the outcome of the event we're looking for. So some added information in terms of note taking. Okay, this is important. What has just been used with the tree diagram is not the additive, but what we call the multiplicative principle from counting. Right? So independent events, as you can see here, they have no influence on one another. So what we say is, in general, okay, so the probability of it being even and tails depends on the number of those specific outcomes observed divided by the total. Okay, so that can be broken down into the following. Okay, so the probability of the compound event is that of each simple, the probability of each of the simple events. So we can take the number of even, that is the probability of even, and multiply it by probability of the flipping tails. So we can see in this case, the chance of being an even roll is 3 on 6, and then the probability of being tails is 1 on 2, or 1/2. So giving that lowest form, probability of 1 out of 4. Okay, so that was the first problem. Now let's contrast that against the second one, and you'll find that problems 2 and 3 are specifically different from the first one. Okay, that is the type of principle being used to solve it, or the type of event being modeled. So let's keep an eye out for that. Here is the next one. Okay, so in this case, you were required to determine the event of rolling a sum of 2. Okay, let's see, is it 2 or 12 or 2 and 12? 2 or 12. Okay, so a sum of 2 or 12, the word or being very important. So you can see through the addition table for rolling 2 6-sided die that there are 2 sums, one here, okay, corresponding to a sum of 2, and only one other to that of a sum of 12. So the fact that we're rolling a 2 and that we're rolling a 12, we can say that those are 2 different events, and the events themselves are mutually exclusive. Okay, so to be mutually exclusive means that the outcome of one, okay, does not have an impact on the other. Okay, so we can see there really is no overlap between when you're rolling 2 1s to create a 2 and 2 6s to create a 12. None of those particular values are shared by the other sum. So mutually exclusive events can be modeled by a Venn diagram, in which I'm going to show here in a moment. And here is that diagram. Okay, so graphically, you can see that event A, rolling a sum of 2, is occupied here. It has its own event space, whereas B, the sum of 12, has its own. Okay, and both of those events are contained within the universal or the sample space. Okay, the symbol here below, okay, actually this statement here, we're going to see what that means. Okay, this means the probability of A, and this upside down U meaning and. Okay, so A and B. Okay, there are no elements within that set. Probability is 0. Okay, the number of elements within that, this symbol here is known as the null set. Okay, so sets A and B share nothing in common. Moving forward on that, the additive principle, okay, for mutually exclusive events, this is the probability of A or B. So the upside down U, or rather the U, not the upside down U, but rather this symbol here means or. And in this case, because they are mutually exclusive events, we simply add the individual probabilities. So that is 1 on 36 plus another 1 on 36. And in lowest terms, that is equal to 1 over 18. Okay? So this is the additive principle for events that are mutually exclusive, and read as the probability of A or B. Okay? Differently up here, this symbol here represents the intersection of 2 sets. So that would be the overlap. And because there is no overlap, we say that it is equal to the null set. They have no elements in common. So let's move forward here. I created another little diagram that you can include in your notes to indicate the null or the empty set, okay, which are the number of elements in the intersection of A and B, okay, and with no overlap, they're mutually exclusive events. So you can already see, reflecting here, that with probability problems, one of the key steps, okay, it's not the calculation, okay, it's very far removed from being successful. What you need to do is to look at the variety of scenarios and determine what type of event it is. Okay, that event will then lead you to the appropriate problem-solving strategy. So what tool what graphic organizer, that is diagram, or what formula or formulas am I going to choose to help me with this problem, okay? And if I can't seem to find a tool, then can I simulate or experiment with the probability using my skills with Excel or some form of physical type of experiment or simulation that I can run, okay? Last but not least, let's have a look at the third scenario, okay? That is the rolling of 2 die. So here we want to determine if a 4 or a pair will occur. Okay, again, the word or being quite important to us in terms of our strategy. Okay, and you might also want to take a moment to think this one through. Okay, think of it in terms of between these two situations. You know, think about the nature of them being mutually or non-mutually exclusive. So just disregard that notice there, guys. Okay, mutually versus non. So having thought about that, let's check it out. So if you take a look at the table, okay, right away you can see that the sum of 4 and, okay, rolling doubles, there is one element in common, and you can see that right here. If I highlight that right now in a nice bright pink, this element right here, okay, that 4 is shared by both event spaces, right? So what we're going to have to do is take that into account. So reading here through the second paragraph, you can see that it's clear that the events are not mutually exclusive, right? So the number of elements in the intersection space, right? The number of elements whereby we have a pair and a sum of 4 being rolled is 1. That is that one single 4 or sum of 4 here, okay? The issue there, okay, have a look here. I'm just going to underline this for emphasis, is that that sum of 4 is being double counted, okay? Bit of an issue, okay? So we don't want to count that thing twice in our calculation. So according to a Venn diagram, here's one for the additive principle for non-mutually exclusive events, or that is event spaces that are not disjoint, okay? They do overlap, and that is where that 4 happens to be housed. So as far as an algebraic representation of the diagram, we have here what is called the probability of A or B, and you can see the difference now. When you do have a shared element between the two sets, it's not a simple matter of adding the two probabilities together, but you must also subtract out the probability of that particular outcome that's being counted twice, which is the sum of 4. So we're going to add the 6 doubles out of a total of 36. To that we'll add the 3 sums of 4, and then we'll subtract out the value that has been double counted, okay, giving us a probability of 2 out of 9, okay, that we're going to roll a pair or a sum of 4. So right now, going back, great idea would be to label these 3 scenarios. Number 1, okay, we have probability of independent events, okay, and that particular scenario utilized a tree diagram and the multiplicative counting principle, and we're going to come back and review that in a later section. Situation number 2, these events were mutually exclusive, okay, and required the additive principle for the union of 2 sets. The third situation utilized the additive principle of counting for the union of 2 sets, but also this was a situation where the events produced outcomes that were non-mutually exclusive. Okay, they shared an element in common. Okay. So let's close the video down here at this particular first one, and then I'll upload a second one that will run through a couple of examples on the use of 2 principles in solving problems.